G'day guys, it's just a follow-up on the last video about this detector, the SD2200D, and after replacing the input stage, you might notice that in here, well, there's no vertical transistors sitting up in the air. The 2SK216 is gone, and also I think it's a ZVP4424 P-channel device, and they are no longer there. So anyway, the detector's working quite well. I'll use a 0.1 test target. So it works very well on the 0.05 too. So I'll give that one a go. So yeah, it works on small gold as well. I've got it on a cancel coil at the moment because these things have only got single input channels, so I can't do cancellation. So yeah, I'll disconnect. I'll turn him off. If I can see the switch, there it is. Whoop goes the detector. Now I'll move this a bit so I can get in. I'll take out my plastic Sharpie. Take off the coil. Take off the power. These things are just a bucket of wires. I've got to glue that back in there, but that's easy enough. I had to remove it all had gunk under it. But on this, if you can see, and make sure I don't touch around the bitey bit there, that'll send me cockeyed. If you can see here, I've got a 2SK1334 in there, and I've put the other device, the P-channel one, in there, and I've had to put a few jumpers on and fix up the through plates. Gave it a dose of white paint so it's all sealed up and nice. But the way to do this, guys, if you want to do this and do it properly, I've done a little whiteboard drawing here, so we'll change position. If you can see there, I'll zoom it in so you can know what's what, and I'll tell you what I'll replace with what was there to start with. It's not very tall, is it? Oh dear me. Hang on, I'll raise this up because it looks weird pointing up like that. I'll try. Hang on a sec, I'm going to move it. To do this with this gadget, it's really difficult. There we go, I'll get that up. There we go, up in the air. And we're going to lock it, else it'll come smashing, crashing down. Okay. If you can see that should make some sense. Well, hopefully it makes some sense. Okay. Little square rectangles. Actually, I should get in there and point at it. So you know what I'm talking about. I think I've got everything there, haven't I? Yeah, there we go. Yeah. I'll have to get past all these detectory things. I'll use a whiteboard marker. I'll take my 4 eyes off. I don't need that. And like, there's never anywhere to put anything in this place. Every surface has got stuff on it. So you go here. These are the parts we've replaced. That one there and that one there. Now basically you can work out what's what. There's the receive coil, you know, at the end of the cable, so that's a coil plug there. So all you do is you've got to find the wire that comes in there, blue wire actually on the SD2200, comes in, and you'll be able to check for continuity between where the coil comes in on the blue wire, and that point there on the board will be the drain of this MOSFET. So it's an N-channel MOSFET. What's in there is a big old clunker of a 2SK216. That's what's in there. So that's been removed, and we've put a 2SK1334, which is a far more better MOSFET by far. That's what they use in all the GPXs, that one. So it'll do the job. They're very hard to get now. They're out of production, but lucky me had a few thousand of them, which I picked up cheap. But they are still around. If you see them, pounce on them, because they're a very good transistor, and you can replace this 2SK216 TO220 package. It's rather big for a front end, and put a little surface mount in there. So all you really need to do is remove this, and with the little surface mount package, normally they go gate, drain, source. They're all the same, most of them. Most of them, they can vary, but and all you do is you put the gate to that point, source to that point, drain to that point, and it won't be the same. These 2SK things, the 216, I mean, the 216 is a really weird pin out. You got drain, source, gate. Now, there's not many devices with that configuration in field effect transistors, but this one has. It's really strange. So what the best thing to do is on here is hook up, say, the source and the gate to these 2 points, and then the drain on top of the little MOSFET, because the MOSFET looks like this. I'm not very good at drawing like this, but it looks like that, and it's about the size of an ant. So we've got a gate, drain, and source there. So what you're basically doing is you get the gate and source. So stick the gate there, the source there, and the drain, when it's sticking out here, just run a wire through onto the drain. Just there to there. So that is how you do that. The little tiny vertical other transistors, a P channel. It's usually, or it can be, it could be other things as well, but a ZVP 4424 will work, or it might be a 44. No, it is a 4424. Of course it is. That is in this position here. And also, if you have a look at the configuration, gate is in the middle. Normally with all these things, gate is here. Go gate, drain, source, but these things are different for some reason. The gate is in the middle. Source is this one, goes to the input op-amp, non-inverting input. And the drain on this one comes off the source connection here. So always just check to make sure you got, this is how you tell which one's which. Whichever one of this one goes to this one, you'll know that's the source and that'll be the drain. That's the way it goes. So just remember, tip the source down the drain, there's your drain, and it comes out here. So back into the drain, and your source comes down to the bottom and comes out. So that's the way you remember them, which way they go. The gates are turned on and off in relation to the transmit pulse and all that timing. What you'll find if you measure the gate connections with an oscilloscope, this one is a complete inversion of that one, where this one's up and on, this one's down and off. And when this one is up and on, this one is, that waveform is the other way around. So whatever the waveform on this is, it's the opposite on that. And the reason is they're both switching the same time, but this is a P channel and it needs the gate signal inverted to turn on. So basically with the N channel, you give it a positive signal and it turns on. With the PFETs, you let it go negative and it turns on, positive turns it off. So it's basically doing this business, but they're both like this on at the same time. You can reverse the polarity here if you really wanted to. Connect up the gate to the gate of this and run an N channel here if you wanted to do that. But they're set up this way and you don't want to go mucking around too much, cutting tracks and joining. But it's very easy to do. A very good device to put in here, which I found, was an RSM002. And the most important bit on the end, P03. If you get any other letters here or numbers, it might be the N channel version, and it will not work in the circuit. You'll just get leakage through the diode. It'll sound horrible, and you'll get no signal strength whatsoever. So, because they've got a body diode in it, it will conduct. But anyway, what you want to do is make sure it's an RSM 002 P03, and that can go in any of these series detectors, any SD that has the NP switching arrangement. So we've probably on this, we've probably got rid of about maybe 15 ohms of series resistance. The signal comes in from the coil. If you've got these things with high resistance, well, 15 ohms isn't much, but what happens is you've got X amount of signal, and 15 ohms will make it degrade. It'll lower it down in its amplitude, and also it actually, well, technically increases noise, but 15 ohms isn't much to worry about. And then it goes into your first amplifier stage. So what you do, if you put the RSM 002 P03 in here, and you put the 2SK1334, you might only have what 1.4, maybe about 3 ohms. So 3 ohms against 14, 15 ohms through this arrangement. So anyway, that's how you do it. If you want to know how the front end works, and don't put transistors in this way or that way, or all around the wrong way and whatever. So yeah, you can always do a freeze frame on that, zoom in, and know what's what. I'll just write coil up there, and yeah, that's the configuration of the 2SK1334. You got to remember the size of that thing is probably about that. That is how big it is. And this one too, it's about that as well, something like that. Whereas the other device, which is in there, the 2SK216, is about that, with 3 legs on it, and that one there, something like that, with 3 legs on it. Oops, that's a bit wonky, but anyway, 3 legs. So that's just sizes of device, going from that size there to that, and that size there to that. So yeah, far more efficient, better packages, less inductive lead length, stuff like that, a lot less capacitance, lot less resistance, far better devices. So anyway, that's that. I thought I'd put that there in case anyone else wants to do this and does a bit of a, a stuff up. Actually, what have I got there? On the computer, you can see there I've actually got the specifications for the RSM device. Oh, that's loose, isn't it? Oh, it's been around. There we go. Now I know what's going on. If you have a look there, have a look at the input capacitance. To drive that FET on and off, 30 picofarads. It's very low. We have a look. Output capacitance is 4 picofarads, extremely low. Reverse transfer capacitance, 5 picofarads. And the rest of it you don't really want to know about. It doesn't really mean much. Yeah, it turns on really fast, like 40 nanoseconds. That's full time. 40 nanoseconds, that's really fast. Turn off delay, 30 nanoseconds. And rise time is really fast, isn't it? 5 nanoseconds. Turns on like bang, she's on. So that's that P-channel device. People don't like P-channel devices. They think that they're inferior. They've actually got lower noise than an N-channel, but they do intrinsically, for the same size device, have greater capacitance. But I'm not going to complain about 30 picofarads gate drive and 4 and 5 picofarads anywhere else on the circuit. It's not going to come into play. And yeah, it's a very, very nice device. So yeah, way up in the air here and spinning around. So that's that. But SD up and going. Let's go and hot melt glue, of all things. That's how they do it. The core. I'll tell you something about these two, which, because a lot of you guys want to experiment. You want to know about this stuff. I'll just wind this back down. or can it just fall naturally? Okay, we're going back down, and then jams up. Oh, it's going back down. Good, that'll do. Okay, I'll show you something about these core things. Get in here. I can't get too close because I can't get to the bench. Yep, if it is. I'll zoom in a little bit to make it easy. That core is on the transmit receive line to the coil plug here. This thing. On a lot of detectors, well, if we have a look at all the GPXs, the coil wires just go through that one time, okay? And what happens with this one, it goes through 3 times. And it's not just 3 times more inductance, it squares on itself, so it's a hell of a lot more inductance. And in later detectors, they don't do that. And I'll tell you why they don't do that, because you lose some of the high frequency signals, fast decay signals. If you actually redo the wires, take them off, either on the board, don't get them muddled up, it'll blow up the detector if you get them muddled up, but put them back in the same spot, unwind it and just leave maybe one whole turn through it, and the receiver will be more sensitive, and it doesn't really make much difference on the noise, because I've never found it to have any great effect. These things here, you know, they're acting as a choke, but they're only really active well over probably 100 megahertz or something of that nature. It's well out of the passband of the detector. But I think what they are there for, well, in my opinion, okay, I'll say that, is for EMC compliance. Basically, slowing down the sharp transitions on the transmit waveform to meet EMC compliance. So, saying that, yeah, it can't have any more of a square wave than the other detectors. So why has the other detectors only got, you know, the wires just go through it, and they don't go round and round and don't do anything like that. I can't see the difference between the later detectors just with the wire set going through once, and why these are going through many times. I'd say that the EMC compliance will work exactly the same, even if you just put the set of wires straight through. But maybe it was done as a some sort of an attempt at reducing noise to the detector. I don't know, just my opinion. And yeah, you can study it more if you want. You could even pester Mindlab and ask them, but they probably won't tell you. I don't know. They might tell you, might not. Ask a dealer and see what they say. But yeah, I'd say it's for EMC compliance. But even if so, that many turns, it's exactly the same sort of transmit system. The newer detectors have more volts going out of it too, so you know, and they're running faster. So square wave issues would be greater than these old clunker chunkers. And I don't know why. I'd just say it was probably on there for EMC compliance, and they said, "Oh, we'll put a few more turns on it, and see if we can get rid of some of the terrestrial noise." But like I say, it's the front end of this does not go up into the megahertz. It's a very, very pedestrian input stage. On these, I think it's just an NE5534 op amp. I don't think these had AD797s in there, but even so, an AD797 puffs out probably around about get on about 50 or 60 megahertz at their 3 dB point, so they fall off really quick after that, and you know, nothing much above the choke cutoff of those is going to get amplified anyway, so I don't even know what it's there for, except if it's EMC compliance. What people have done, and I'll tell you this, and don't do it, what some people have done is left this on the transmit wires and they've completely taken the receive wires and bypassed the choke and connected it up. Believe me, that is one of the biggest problems you'll ever create for yourself. It will throw everything out the detector rack like an absolute cow of a thing, and you will have absolute no end of trouble trying to ground balance. It'll just basically cause a bypass looping effect, and you'll have different rates of signals coming in, getting delayed, and straight is not, and things won't line up, and it'll be absolute dog's breakfast. So if you're going to put chokes on these things, make sure all the wires from the transmitter and receiver, both, whichever go to the coil actually, go through a choke if you're going to use a choke. Normally I've seen these, and in the long distant past, they just chop the whole thing out and don't have it there. It makes for a more sensitive receiver, but yeah, you should have at least the cables going through it, or even one complete loop turn. I think that's 3. You can probably back it off quite safely. I'm not going to tell you that it's still within EMC compliance doing that. Up to you what you do, and I don't suggest it. Then how's that? I don't suggest it in my opinion, but it does make the detector work better. And yeah, and this thing here with those new parts, I tell you right now, it would be far more sensitive and more snappy on very, very small gold. Far better than what it was. So you can, like I say, and the other thing you should do in here too, no, I'm not going to say it because the guy who did that, Bizzo, might go and have a go at the power supply and might come back here. But that's a joke. But it's probably true. But you could do the synchronized power supply on this as well, because it has a free running power supply and it's generating crud straight through the receive windows for the receive signals coming in. But like I say, up to you. It's a very similar system. There's different takeoff points. You haven't got those what we call test points on the SD2200. You actually have to go and measure some of the components to work out where you get the signals from and what you can flip and whatever. If I actually look in here, I can't even remember. It's got a 40106 in that area. It might be a different configuration. I'd say it has. There's yeah, one of those will probably be one. But you know, you can't work out what these are, because if you take the paint off, all the numbers are scratched off the chips. So you're going to have to actually sit there with an oscilloscope, scrape the paint off the legs and measure them, and then just work out by a simple truth table what they are. I mean, it's been done many times, but that was you know, IP protection back in the day. Rub the numbers off everything, and now you just do it with a microprocessor and burn all the internal fuses, and you can't read it. Well, supposedly, but I could tell you a story about Atmel chips, but I won't, because they didn't want me to repeat it, what I told them once upon a time. Yes, so that's that. It's all up and going. It all works. And yeah, I pinched that back out. Couldn't see what I was doing then, if things were in view or not, because I wasn't behind the camera looking. But anyway, that's how you do the front end correctly. So if you follow the diagram I did and replace it with those parts, you'll have a better detector. And yeah, anyway, it's enough of that. I want to go back into you know, what we call it, a bit of a dumber mode, chill mode. I don't want to keep straining the brain on this stuff. Chill out and take it easy. Catches.